This is CPhO 39's question 5, and this problem is one of the most interesting question in this exam. So let's go over the problem first. So basically the problem is saying that there are like basically two springs over here. And between the springs, there's a small ball with mass of m. And if you apply a force to it, like there are two conditions or two ways that springs can be broken. So the top spring, and we call this 1, can be broken first, or the second spring at the bottom can also be broken first. So the problem is saying that if you like apply the force or increase the force very slowly, there's a good chance that one will be broken first. While if you pose a spring very hard, the second spring is probably going to break first. That's what the problem is saying. So let's take a look at question A. So for this one, we only need to write out the Newton's second law, which is mass times acceleration is equal to the total force applied to the ball. And in this case, there's gravitational force and there's spring force, which is pointing up. And in this case, we choose the downward direction as the positive x direction. And we can see mx1 double dot is equal to this bunch of stuff over here. And that is basically question A. And now let's move on to question B. So for this one, we have ft is equal to this when t is greater than 1, while it is equal to 0 when t is lesser than 1, right? And it is asking us to find the value of x1 as a function of t and x2 as a function of t. So how do we do this? The way we do this is also write out as the Newton's second law, and we can see that the equation becomes this bunch of stuff over here. And this equation is actually kind of difficult to solve, but that's not really. I think the difficulty is medium, but the way to solve it is kind of hard to think of. So the way we solve this is set x1 to be equal to two parts, and we call this first part x1 prime, and notice that this prime is not a derivative, but it's just basically a notation over here. And plus the second term, x1 star. And now we set the equation to be mx1 double dot prime plus x1 prime is equal to 0. And x1 star times k, 1 is alpha t minus mg is equal to 0. And if you're interested, you can plug in the equation back to here, right? You can plug in back and you can see the equation is satisfied. And for the first equation, we can get x1 prime is actually equal to a cosine omega t plus phi, and where omega is equal to the square root of k divided by m. And how about x1 star? Solving this equation, we'll actually get x1 star is equal to alpha t plus mg divided by k. So now from this, we can just plug in back to the original equation, and we can see that x1 is equal to this bunch of stuff over here. And now let's consider the initial conditions. So what's going on at initially, right? Initially, the spring is at rest. So there's only gravitational force and the spring force applied to the ball. And the forces are balanced out. So that is telling us mg is equal to kx1. So x1 initially is equal to mg divided by k. And so we will have this equation over here. And how about the second initial condition? The second initial condition is saying that the ball is not moving. So the speed is equal to 0. So we'll have x1 dot is equal to 0. And now we just need to plug in when t is equal to 0, and we'll get a cosine phi plus mgk is equal to mgk. And from this equation, we can get two values for phi. The first one is plus pi divided by 2, and the second one is negative pi divided by 2. Now let's move on to the second case. So, or the second initial condition, which is over here. And when we plug in t is equal to 0, we can get negative omega a times sine phi plus alpha divided by k is equal to 0. And something to notice here is that omega, a, alpha, and k are all positive. And if we reorganize the equation, you will see that sine phi is actually greater than 0, right? And if we plug in phi is equal to negative pi over 2, you can see that sine phi is actually is equal to negative 1, which is lesser than 0. So we can just cancel or eliminate the case where phi is equal to negative pi divided by 2 and keep the case where phi is equal to pi over 2. So now, let's see. From this equation, we actually can get a is equal to alpha divided by omega k, right? And then let's plug in back to the equation, and we can see that x1 is equal to this term over here. And how about x2? For x2, because the spring is massless, the tension throughout the spring must be equal to Ft, right? So in general, the spring at two sides, there's Ft in total, right? So using Hooke's law, we can see that x2 is actually equal to Ft divided by k, so which is equal to alpha t divided by k. And now let's move on to question C, which is the more interesting part. It is trying to find the range of alpha corresponding to spring ones that must be broken first. So how do you do this? So for x1 to be broken first, x1 must be greater than x2, right? So we write this condition over here first. And if we just plug in the equation and do some cancellations, we'll get this equation, which is greater than 0. And because for all time of t, right, for all time of t, spring 1 must be broken first. That means this equation must be satisfied at all time. This equation must be satisfied at all time. And now let's figure out what is the range of absolute value of sine omega t. So that is basically lesser or equal to 1, right? And when you set sine omega t to be equal to 1 and move this term to the other side, we'll actually get the condition to be equal to this. And now you can see that alpha is lesser than omega times mg. And let's move on to the second part, which is saying that for the value of alpha that does not necessarily cause the spring 1 to be broken first, analyze the conditions that must be satisfied at moment t, 0, that cause the spring 1 to be broken first. So how do you do this? Because this case is different from x1, alpha must satisfy the condition which is greater or equal to mg omega. Now let's see what's actually going on over here. So let's draw a graph first. Just let me copy this graph. That's not going well, so let's just do the problem over here and see what's actually going on. So first, we draw a graph for x2 as a function of t, and you can see this graph is basically a straight line, right, with slope of alpha divided by k. And how about x1? At the start, x1 is at mg divided by k, right? And you can see the slope over here is actually also equal to alpha divided by k. But there's a term which is negative alpha divided omega k times sine omega k. So the graph for x1 might look something like this. right? And when x2 is going to break first, and if we draw the graph, when x2 is going to break first, the time is probably between like this region, right? Or this region over here. Or this region. So for this, we're going to figure out what is the conditions. Let's go back to the problem. So if we write out the equation, we'll see mgk divided by k is greater than this term, right? And reorganize the equation, we can see sine omega t is lesser than omega mg divided by alpha. And you can see that because alpha is greater or equal to mg omega, this term is actually equal or lesser than 1. And let's figure out the angles. So for this problem, because we want this sine omega t to be lesser than this, and where we plot out where y is equal to omega mg divided by alpha, we're only interested in the area or the parts where the angle is basically between this part, and we're trying to figure out what the angle is. So now let's consider what this angle theta is, which is the angle between the x-axis and this, right? We're basically trying to figure out what this angle is. And from this, you can set sine omega t to be equal to omega mg alpha, right? And now you can see omega t is actually equal to arc sine of omega mg divided by alpha. And to find the angle, we basically need to plus 2 pi n by theta. And so the angle must satisfy these two conditions. Now let me explain why. So for this first part, this part is this part, right? And how about the second part? Where the second part is basically this part. So what is the angle over here? The angle over here is 2 pi n and plus pi and minus theta, right? And how about this angle over here? The angle over here is basically 2 pi n plus 2 pi. So let's plug in back and see, and we'll get this condition over here. And we need to write out the conditions for n. So the condition for n is that n begins from 0 and to 1, to 3, to 2, and to 3. And that is basically problem 2. Now let's move on to question 3. So is finding the relationship between possibility of spring 2 to be pulled off first and the value of alpha, and use this relationship to explain the experimental phenomenon in this problem. So for this problem, we only need to figure out the case where sine omega t is greater than omega mg divided by alpha. So basically, we're trying to figure out when the angle lies between this region, or basically when the angle lies in this region. And from the graph, we actually can see omega t is between this bound, right? And for this problem, if we pull like very hard, alpha is actually really huge, right? And when alpha is really huge, this term is really, really small. So arc sine of this is approaching 0 when alpha goes to infinity. And what happens is that if theta is small, this range will expand, right? This range will expand. And that corresponds to the greater probability of x2 to be broken first. And that basically explains the phenomenon in this problem. And let's move on to question D. And it is saying that it's given a critical length to ensure that spring 2 is pulled first, and try to determine the relationship that alpha needs to satisfy. So for this question, it's relatively simple. We just need to plug in the equation. So we'll have T0 is equal to this, where we, in the previous problem, we found that x2 is actually equal to f t divided by k, right? Which is equal to alpha t divided by k. And from this, we can get T0 is equal to k L divided by alpha. And for spring 2 to be like pulled off first, this condition must also satisfy, so we only need to plug in and see this is basically the solution for this question. And now we are trying to figure out if both springs, if like there's a possibility, if like both springs can be pulled off at the same time. So if they're pulled at the same time, the difference in x is basically equal to 0, and which is corresponds to this function over here. And if we plug in T0 is equal to this, we'll get if this this and this are equal to each other, like x1 x2 will be broken at the same time.